Allow me, we can, let me first, today our guest is Professor Youssef Ouknine. Let me just give an overview of his background and welcome him to this seminar. So Professor Youssef Ouknine is actually affiliated, has actually three affiliations. So he's based in Cadi University in Marrakesh, and also in Mohammed VI Polytechnic University at the Africa Business School in Rabat. And he is also a resident member at the Hassan II Academy of Sciences and Technology. This institution is the prestigious one in Morocco, who provide funds for researchers and very well established professors. So Youssef Ouknine earned his PhD in mathematics from Pierre Marie Curie University in Paris in 1987, and followed later, a few years later, by Doctorat d'État from Ayyad University in Morocco, Marrakesh, in 1990. So since then, he became a professor at Ayyad University, and has became affiliated to the Mohammed VI Polytechnic University since 2018. And of course, concerning the Hassan II Academy of Science, he has been a resident member since 2006, since its creation, in fact. So he has chaired a lot of committees, in particular the jury of the Concours d'Agrégation de Mathématiques since 2016. This is, of course, organized, I think, in coordination with friends. And he is a founding member of the Excellence Center, recognized by the ERCE label from the European Mathematical Society for 2 periods. The first one was from 2006 to 2020, and the second one extended for 4 years, from 2021 and 2025. So he has been also elected recently to the World Academy of Sciences in 2024, as based on his or as a recognition of his contributions in mathematics and the probability in particular. He served also as a scientific board, including CNRS, sorry, in Morocco, and also in the Academy of Science, the Hassan II Academy of Science and Technology, for many activities. He previously directed the school, the National École Nationale des Sciences Appliquées à Marrakech, in Marrakech, and he also supervised more than 30 PhD students. Most of them are Moroccans, but there are also some from some countries in Africa, like Cameroon, Gabon, Senegal, many African countries, Central African countries. So he has been served also as a member of the Scientific Steering Committee of SEMPA for 8 years, and he has been invited as a speaker in and collaboration from renowned institutions around the world, in particular in Europe, in Japan, China, many other countries, as I remember. And lastly, his research focus on particularly on stochastic analysis, probability theory, with significant contributions in stochastic calculus, optimal stopping, Malevin calculus, and mathematical finance. So Professor Youssef, you have the floor, and today's talk will be backward stochastic differential equation with central value reflection. You have the floor, Professor.
Thank you, Professor Eddebi, for this introduction. Can you hear me? Is okay?
Yes, perfectly.
Okay. Thank you very much, Professor Eddebi. Yes, I thank you, sir, Professor, all of the audience, Professor Wissam Jdidi and Professor Rafiq Aidesh. I met them before in Tunisia. Yes, I supervised more than 30 PhD doctorate. Mohammed Dabi is one of them. Actually, he is one of my my students. I think the second or the first one when I come to Marrakesh. And I'm happy that I see you very well in Saudi Arabia. I want to thank the audience and excuse me for my English. It's in the average, but maybe the slides are well written by my PhD student Kautar Nasrullah. In this talk is based on a joint work with her. Is called the backward stochastic differential equation with central value reflection. It is a recent work done this year and is based on the following publication called backward stochastic differential equation with central value reflection, which will appear in probability uncertainty in quantitative risk 2020-25. We discuss some, this is a technical topics, but I will recall some definition in some tools needed to attend this conference. And after I will send you the slide in publication, full publication if you want. Let us recall what is the difference between SDE, stochastic differential equation, in BSDE. There is a B, more backward stochastic differential equation. In SDE, is introduced by Ito. It's something like this. We give the initial condition. It means that we are looking we are given some this Brownian motion, some two coefficients. This one is called diffusion coefficient and one is the drift coefficient. And we have the dynamic of our process is like this one. This is the stochastic integrals with respect to the Brownian motion. But the main difference between backward and forward is that for the forward, we give the initial condition and we are looking for adapted processes. It means that we move from 0 to time t forwardly. And for backward stochastic differential equation, we move from the terminal condition from time t to 0. Okay? This is the difference between these two things. For the stochastic differential equation, it's something like this. It is written also as integral form. It means that xt is equal to the initial value, suppose it's some random variable, square integral random variable, which is 0 measurable, some this Lebesgue integral and this Ito integral, and we suppose some condition on Lipschitz condition satisfied by the coefficient u and sigma. We can prove the existence and uniqueness, and this solution is adapted to the sigma algebra generated by the Brownian motion in x0. Yes?
No, it's okay.
No, continue. Good.
Okay. Thank you. And we ask this to be adapted. It means that xt is a functionals, measurable functionals of some of ft, or when we call strong solution. It means that xt is a deterministic functionals of some x0 in the trajectory of Brownian motion up to time t. Means that not anticipative. Okay. And for the backward, now I go to the backward. We are looking for some y and z. I will explain why this comes in the picture, because we can't solve backward without this adjoint process. This is an additional process introduced by Bismuth in 73. Okay, and in this one we give the terminal condition is square integral, which if capital T measurable. It means that we give a terminal condition and we look for the initial condition. Now we look for the initial. Here we look for the initial condition and we give the terminal. This is y. This is y. Excuse me. This is y. Y capital T y capital T is equal C, and we are looking for yt to satisfy this equation. We are looking for two things, for y in z, such that this equation is satisfied. This one is called generator of the equation or the driver, and this one is, you know, this is one equation, but you have two unknown process, y in z. This line contains two unknown process, y in z. You have one equation and you have two unknown process. And this is well posed. We can prove if, for example, if is at growth as a linear or and f is Lipschitz, then we can prove the existence and uniqueness in adequate Banach spaces of processes y in z. This one is predictable square integral. I will call the space process. Satisfy this condition. It means that yt, it's written from t to times capital T. Y at every time t is equal to this terminal condition, plus this Lebesgue integrals minus this stochastic integrals. There is only one process, adapted process, y in z, such this equation is satisfied. Is something is strange, because you have one equation, you have two unknown, but this is done by the so-called representation theorem. And this representation theorem tells us that every square integral martingales is a stochastic integrals. It means that in Brownian filtration, every square integral martingales is stochastic integrals. It means that in particular, every martingale in the Brownian filtration generated by W can be written some stochastic integrals. It means that these martingales are continuous. All the Brownian martingales are continuous. They are looking for this adapted. This is very important. We give the very important because the adaptedness is done by the help of the process Z, this control. Without this Z, we can't. I will give you a counter example that without this Z, we can't have the solution of, because you have the anticipation here. You have the yt is equal C, yt is equal C. So you don't have a chance to have something which is adapted, because we have some anticipating condition. By the adaptedness comes from this adjoint process is absorbed. This is the help. This is Z help us to make Y adapted, and this has an interpretation in mathematical finance. We can prove that this is the value of some portfolio, and Z is the okay is for the hedging. Okay, and this is, we can prove that the first one will prove this in the linear case when F is some linear affine with respect to Y and Z is done by Bismuth 73. And the first one who got this result in the case of F is Lipschitz, is Pardue-Peng in 90. And after that, he has a lot of applications in PDE, in control, in finance, everything. Okay, but we are looking for some couple Y and Z satisfying this condition 4. Condition 4 satisfied by these two processes, Y and Z. Okay, this one is called the control.
Please, can I ask a question, please?
Yes.
In the slide 4, what is the function F? Maybe you have
this one.
Yes, the function F. Yes.
This function F is some given function called the driver. Is some given function. Okay, which is ft progressively measurable in some Lipschitz condition. This is given. This one is given for our this one is given.
Okay. And by adapted the process, you mean that for all small t less than capital T, y of small t is ft measurable.
Yes.
But y of small t depends on zs, where s is bigger than small t.
But excuse me, why?
But y of small t, by using equation 4, it is given using zs, where s is bigger than small t.
Yeah, but there's some cancellation. There's some cancellation here. You have this is the idea is the representation theorem. Is very simple. First, we solve the problem when f is equal to 0, and we have some representation. This is the representation exactly when f is equal to 0. This is the representation theorem of the martingale's expectation of c with respect to ft. Obviously, ft is generated by the Brownian motion. Okay.
Okay. You mean f? You mean t small t or capital T? Ft is t is small or capital?
No, yt, this one, okay,
okay.
This y is ft measurable, small t.
Okay.
Ft measurable, okay. This is done by the martingale representation theorem.
Okay. Thank you.
Okay. Thank you very much. Okay. I will give the idea of the proof. Is very simple. It's based on a fixed point theorem in the martingale representation theorem. Okay. Let us consider this counterexample. Let us consider this equation. When dyt is equal to 0, but this capital T is equal to psi, when psi is ft random variables. But the obvious solution of this is yt is equal to psi, because this is constant. But yt, if we put yt is equal to psi, then this one is not ft measurable, because it's only this one. If this is not a solution, because we can't have a solution with this. It means that we need the adjoint process. We need the process z to make y adapted. Without z, we have a counterexample. This equation, the obvious solution of this equation is yt is equal to psi. But yt is equal to psi is not a solution, because we need that yt is ft measurable. Okay, the solution is not adapted to the underlying filtration. It means that for backward stochastic differential equation, we need some extra term which makes ya adapted. Okay? And this is the basis for the excuse me, I'm talking for all the audience, but this is the classical in backward stochastic differential equation. The starting point is this: if psi is co-integrable random variables, which ft measurable, then we have this. Representation. It means that when ft is the sigma algebra generated by W, then you have this martingale is equal to its mean plus some process. In this process z, it comes from this representation. Our process z, it comes from this representation. Then there exists an adapted pair of yz which satisfy this. If you take, for example, xi f capital T measurable, we write this for psi, and you have this is satisfied. It means that you have a backward equation, dyt is equal to zt dwt with this y capital T xi. This is a backward equation which introduced. I told you that z serves only to have this y ft adapted, and we have the solution of this is yt is equal to the expectation, conditional expectation of psi with respect to ft. This is the simplest one. It means it corresponds exactly to the case where f is equal to 0. And this is general case also, because we will prove that this is sufficient to solve some Lipschitz backward stochastic differential equation. Okay. More general, this is done in several papers by maybe several by Bouchard, Eli, and a lot of people from Le Mans, from Paris, okay, Marduquin, China's people, okay. We are interested in this equation. It means that now we are interested with backward stochastic differential equation with the constraint on the mean. It means that with this constraint, it means that we want to solve this backward stochastic differential equation with this constraint which you write in red. That it means that for some given psi, expectation of psi yt is greater than n. It means that one classical backward stochastic differential equation with this is a condition on the law of y capital T. This is our starting point. And this one is called backward stochastic differential with weak terminal condition. It means that the terminal condition one just to need some constraint on the law of YT. This is done also in a paper by Hamadan Jehish in another author in Journal of Applied Probability. And we are in this equation, we need to have some in minimal fashion. It means that we need to have some flatness, the Skorohod or the so-called Skorohod conditions. Mainly the problem is to find in y in the control z such that this process is satisfied. This equation is satisfied. This is right in forward fashion. It can be written in backward fashion, and this condition is satisfied with some minimal condition, some flatness. Means that we need to add some increasing process like the Double-Meyer decomposition, or Snell envelope if you want. This is our problem. The problem started, I think, for the first time by maybe Brian, Ili, and Wu. This is called backward with linear reflection, which appear in Annal of Applied Probability, and the one of Hamadan in this quarter also maybe 2022 or 2000, something like this, which for backward, for reflected backward stochastic differential equation with linear reflection in the involving the law of the process Y. This is our guide also. And Brion in this quarter constructed the system, the solution of this system of equations. It means that they are looking for a triplet YZK of backward stochastic differential equation such that this line is satisfied. You have to add some Skorohod term, so increasing process adapted in predictive increasing process. So we take our n is equal to 0, the barrier, and such that this is equal to 0. It means that the process, the support of the measure, this is the Kazakh process, and it means that decay defined a Sturgis measure, and the support of this measure is supported by
يوسف
yes
حاول عفاك ما تحركش هذاك الكيت نتاع الصوت لان كيدير واحد لو بروي
وي
It's a little bit noisy.
Okay. Thank you very much for your remark. And we are looking for flatness. It means that the process, this Sturgis measure, deterministic one, K is deterministic, such that this is satisfied. It means that the measure is with support in the set where this expectation is equal to 0. Okay. Then we can prove some formula that KT is given by this formula. Okay, is given by this formula. And now we suppose our main hypothesis is the following. We suppose that LTY is strictly increasing in a Lipschitz function and locally, I think, and FTY0 is bounded by a constant L, and this one is now this one for in our case is only locally Lipschitz, but this is the hypothesis of Hibon in the view in view. They suppose that this is increasing in Lipschitz. This one is bounded in Lipschitz function, something like this, and they proved existence of uniqueness of this problem. In the setup, this is the Brownian case, but it can be done also for the universe which support a Brownian independent random Poisson random measure in U, such that this Levy measure, this nu is the Levy measure, satisfies this condition. And this one, we note that in tilde is the compensator of this in with respect the compensator is this one. and we are looking for this. Voilà, this is our approach and our novelty in this talk is to solve something like this, but we are looking for some maybe y, z, v, and k, the quadruple process, such this is satisfied, something like a Scholar equation. The function f satisfies some regularity condition, but it depends on the law of ys. It means that the driver depends also on the law. This is solved also by Hamadan Jihish in their I don't remember the third or that. And we in our content, this is our content. Our content is this. We suppose that gamma yt is greater than 0, and this is equal to 0 in a minimal fashion. It means that we are looking for k, which is predictable card lag increasing. This support is on the set is this one is equal to 0. What is gamma x? For this we define the so-called this x is called the Doob constant. It means that we are concerned with this map solving the equation. You take the expectation of arctangent of yt minus x is equal to 0. This is only one solution of this equation in x. It means that for any random variable, which take x, capital X, a random variable, value in R, a real random variable, then you have one. This is the called the mean. This is the called the mean. X is called the mean of yt. For example, if you have the law of yt is symmetric, then you have x is equal to 0. Okay, if the law of yt is equal to the law of minus yt, then you have this x is equal to 0. Then it means that it replaces in what's called the expectation. But here we don't need that x or y has an expectation or something. The Doob number is defined for every random variable, a real random variable. It replaces the expectation. Okay, this is the mean value theorem. Okay, you consider the application of x associated to this. You have is continuous and is derivable, strictly increasing and is continuous. Then you the limit in plus infinity is equal minus p over 2, and then you have the existence of one and only one solution of this equation, and this x is called gamma yt. Yes.
Donc, on recrute un enseignant ou un chercheur. Donc, ça veut dire quoi l'enseignement et le volet technicien.
Alors,
donc, ça peut ouvrir un emploi. Il faut qu'il y ait des feux verts de chaque côté. C'est pas parce que vous
S'il
avez.
vous plaît, essayez de désactiver votre micro. Parce que ça, on vous entend.
Oui, j'ai cru qu'il a posé une question, non?
Oh, c'est quelqu'un d'autre. Je ne sais
Ah,
pas si c'est une
d'accord.
question. Si c'est une question, c'est pas clair.
S'il vous plaît, c'est une question.
Monsieur, vous posez une question?
No question, I think. No question.
Okay. The process K will take the form. Then we consider this K is equal to the supremum of this negative part of gamma ys minus the supremum of this when s is greater than t. This is our K. Okay, this is deterministic because our x is deterministic. Okay, in this equation, our x for every yt, this x is called gamma t is the deterministic function. Okay, and we have excuse me. Then we have the first component. Then we have this. We want to solve this this equation. Okay. Then the function arctangent is only locally Lipschitz. You know, is not Lipschitz function. Then we consider a bounded terminal condition in the driver, which is general quadratic exponential structure, to essential the bounded solution. Is exactly we are in the scope of the paper of Hamadan in Annal of PHP, something like this. When you have the boundedness of Xi, then you can suppose local Lipschitz. This is exactly what is mean this, because the arctangent is not Lipschitz like in the one of who they suppose that strictly increasing Lipschitz, but in our case the arctangent is not Lipschitz but locally Lipschitz. Then if you suppose then our terminal condition is bounded, and we have the BMO martingale theory, then we can prove some boundedness of y in local Lipschitz because Lipschitz is sufficient. This is our mean by in this talk. Okay, let us consider. I will give the main idea of the proof. Let us consider this backward stochastic differential equation with in constraint on gamma number. It means that this one is greater than 0 and this is equal to 0. Then we consider the idea is to consider the case when f is does not depend on the random variable on all the process, and you have some from some representation theorem in the filtration generated by y in t. You have the representation theorem, and you put y bar, z bar, v bar is equal to this after. Okay. Then we have by this we have identification of z in v. This is the solution of our case when f is equal to 0. Okay. Then we recover y. Then if we have y, then we put y and k because k is constructed from y. Okay. Here is this one. Okay. If you have y, this is fs. Then if you have y, then you have this.
الله المستعان.
Okay, let us give our functional space. The S2 and S infinity are the space of progressively measurable Cadi-like processes.
Sorry, I have a question, please.
Yes, yes.
Hi. I want to know why f should be increasing function.
Why?
The driver f is increasing function in the main assumption.
No. Where do I put an increasing function? No. Where?
I saw now in the assumptions. Okay.
No, there is no, because f is only independent of
okay.
of the,
F maybe in the other slide.
No. F
okay,
is
sorry.
the L is increasing function, not F. The L.
The L. Okay.
On the boundary.
I see it F for that.
No, excuse me.
Okay.
No. The L is increasing function because we want to like arc tangent.
Exactly.
Okay.
I write the F for that. I was.
Okay. No.
Okay. Thank you.
Thank you very much.
Okay. Thank you.
There are our functional space. The y is the classical one, is the Banach space with this norm. Ys infinity is equal to this one. H2 is the sum of progressively measurable or predictable process such that this one is finite. And we suppose this space also is the set of P tensorial u, because we have to, this is for omega and t, and this one for u, and such that this one is finite. This is also, all these spaces are Banach spaces. For the triply YZV, this is Banach spaces with this norm, this one plus this one plus this one. Okay, and we add also some need to the boundedness. It is classical also in H2BMO is the set of predictable process or progressive measurable process such that this one would be satisfied. Okay, the supremum over all stopping time of these things, conditional expectation of F2, supremum on omega is less than infinity. And you have this one also, and you have to add the jump here, and this one is finite. Okay, and so we have the set of probability with this moment, finite moment of with P Weierstein distance, which is classical because the space is classical because you use the dependence in law of y. So we have distance between law. In our hypothesis as the following. It's somewhat different from the one of Hamadan and Jaish, because we suppose that this is bounded by a constant m. And there is some, this is the Okay, the boundedness of our generator lies between this one and this one is exactly the one something like proved by Iddabi, which is a continuation of our work with Bahlali. Not so probability, we suppose it means that solving backward stochastic differential equation with quadratic growth, but this one we have some jumps. Okay, this is done also by okay, and we suppose that this is satisfied. This is some Lipschitz condition with respect to y, the variable y and mu, the law, because we have this is py, this is the law, and we suppose that the derivative with respect to z is grow linearly with respect to z, and the second derivative is bounded, and we have this condition to have to answer some comparison theorem. Okay, this one is with Grigorova kinase in the if you have also in other papers, you have some condition like this, using the martingale exponential, then you can prove some validity of some comparison theorem, because you need this to have a convergence. And I want to study this application, this map. I need some regularity of this map. T associate the gamma number, the double number of yt, means that the one which solve, this is the gamma number, okay, which solve the expectation of arctangent y bar moins gamma y bar, okay. Then we put this gamma bar is equal to the left limit of our process. Then we can prove that this some regularity condition to prove that we have some continuity condition, and you have the limit when s decrease to t of this is equal to some regularity condition of this application, because we need some regularity of this application, and application T associate this deterministic number gamma yt. Okay, then yeah, exactly, and exactly the continuous function. Establish the left limit property of the application and the right continuity. Okay, this is Kazakh function, and we have this okay, a quadruple which belongs to this space is said a deterministic solution of our equation with constraint with central value if it's satisfied equation with this okay, with this condition of Skorohod. It means that this measure, this Kazakh measure, is supported by the zero of this number or this function. Okay.
Why, Youssef, why it is called the deterministic solution to 17? Why the word deterministic?
Because K is deterministic, not random. K is deterministic.
K?
Yes.
Reflection.
K, yeah, the reflection term is deterministic.
Yes.
Yeah, it's classical in BSDE with constraint law. Okay. This, yeah, by Hamadan and who, and this one is deterministic. Okay. We know because it's somewhat because the flatness condition is given for something which is deterministic. Look at the flatness condition. They give you K. This one, because this one is deterministic, then we choose K, so is deterministic.
But in the equation, you have something random.
Okay.
Okay.
Yes. Okay.
Is a deterministic flat solution because you have this K is deterministic. Okay. And you have the this is our K, Professor Eddabi. This is our K. It's the supremum of this deterministic thing, but this one is deterministic. This is the double number, the solution of arctangent of y minus x is equal to 0, because this one is deterministic. This one also is deterministic. Mohammed.
Yes, yes, okay. Yeah, I follow you.
Because this one is this number is deterministic. Even this one is random. This is a solution of equation expectation arctangent of y minus x is equal to 0, and this one is deterministic. It's only one x, just the value intermediate value. Okay.
Yeah.
It replaces the mean value. Okay. This is for non. It's equivalent for the mean for the expectation for non-integrable random variable. It's something like this. Okay. Okay. Then you have this flat. We prove this flatness. It means that we have uniqueness of our equation. And from the representation theorem, you have this z1 is equal to z2. Okay. Okay, this is our assume that this condition on Xi is satisfied in the this condition on generator F also is Lipschitz with respect to Z in V. Okay, then suppose that it doesn't depend on Y in the law of Y. Okay, because we want to solve something which is somewhat it depends on Y in V. You have 5 variable, but we start by supposing that it doesn't depend on these two, but only on T, Z, and V. Suppose at the beginning, we suppose that our generator depends only on Z and V. Then you have some in Lipschitz way. Then we can solve this equation by standard calculations in the fixed point theorem, Picard iteration, or something like this. Then you have the existence in the uniqueness, and after that we start our machinery of okay. We can use also the Poisson-Meyer in this quarter result, which proves the existence of this equation is a classical thing when F, because it's Lipschitz, belongs to some L2, and we have this okay, this equation. Now we consider some fixed point theorem. We consider okay. We consider this equation has unique solution with flatness given by this. Okay, this is done in Cadi, what s'appelle Casitani, Poisson-Meyer quadratic BSDE with jumps. Fixed point approach, which is established in electronic journal of probability many years ago. And we use this classical thing to have this is we define an application to gamma. We associate some y. It means that for gamma is given, P of gamma is given, and suppose that we give this red processes, and we consider this backward stochastic differential equation with contrast, and we will prove that this application has a fixed point theorem. It's classical. Okay, we prove that this because when F we have only depends on S and Z and V. Then you use the previous result, and you have the existence of this process, and we know we prove that this phi has a solution, but for small intervals. It means that we will some concatenation. We will this S infinity H is some subspace of H with supremum is taken only on T minus HT. We have the classical result by approximation, not approximation, by concatenation. We solve first in interval T minus H, and H is chosen such that we have some contraction principle, we have some constant which is less than 1, and we start our procedure from T minus H, T minus 2H, and in infinite number of steps we reach 0. Then we have existence of solution in of our problem. Okay, how to choose our solution to have only, but you need this something like this lemma. Okay, we consider the BC bar is the set of such that is the process which belongs to S infinity H, such that the norm is bounded by C bar, and we will prove that phi b c bar is included in b c bar. This is the approach given in the paper of Hamadan, maybe the first paper doing locally Lipschitz in 7 years ago. 20 years ago, perhaps, yeah. Okay. We assume that this we take this constant, and we prove that if there is some constant h, this is the constant h which we should choose in our interval. Okay, we will determine what is the constant h. This one, such that we have, if this is less than c bar, then y, the solution is also less than c bar. It means that we are looking in the bounded interval, bounded domain. So you use only, it's sufficient now that our solution arctangent works. We don't need B Lipschitz, but only locally B Lipschitz. It is Lipschitz in the bounded interval minus C bar. This is important fact, because we have this requires only the locally B Lipschitz in the case of arctangent of L. Okay. For this, we prove that some calculations using some backward stochastic differential equation in the the technical result, and we will prove some estimation of y bar by the help of estimation of this double number. Okay, then you have this one. Okay, then you have some estimation about this. This is important fact. Okay, the estimation of this double number of our y bar. Okay, then we have this. Okay, we have this calculations, and we prove that this is our h c bar is the minimum, the mean of this and this, which is greater than 0. Then we have this. This is important fact. Maybe is this relation. If you have the starting is less than C bar, then you have the solution. You remember the solution corresponding to gamma is also in C bar. This is, if gamma is in some bounded set, then the solution also is in this bounded set. This is very important fact, because it means that we work only on this bounded minus C bar. This is a very important fact. It's 57. These relations, and this h c bar is this small constant. We are working in this interval. This is hc, and we duplicate this relation in the interval t minus h. We start in t minus h, t minus 2h. Anyway, we reach infinite step of we reach the 0. So we have a solution. We have a concatenation. Then we have a solution. Okay. The main problem is this this one. Then we have existence fixed by the fixed point argument, or phi. Then you have this gamma, p gamma can be replaced by y py, and you have is the solution of our backward stochastic differential equation. Okay, this is the theorem which is started in this. Okay, this is some estimation, the step of the proof, some estimation between two solutions, which is calculated with respect to the gamma number, double number. Okay. With the double number, so we have some property of this, and arctangent we use so this arctangent is Lipschitz with respect to this, and but on the other hand, this one is greater than x minus y, and you have some, because the derivative of arctangent is 1 over 1 plus x2, and this one converges to 0, then it can't be Lipschitz, because the derivative converges to 0. But we don't need this Lipschitz, because we know that our solution lives in the interval minus c bar. So we need only locally Lipschitz. We need only this Okay. Then you have this arc tangent, the right you have this one. Okay. Then you have speculation. This is the proof of that our phi is has a fixed point. So we have okay, this is a contraction in the BC bar, the set of processes which less than C bar. Then you have this contraction. Okay, then we okay, by concatenation we choose our h in this interval. We divide the interval 0 to is a classical thing with the length small, and we solve in every yeah, this is the we start after that we start on t minus h, t minus 2h, and we construct our solution by concatenation. Okay. Thank you very much for your attention. I think in time, Mr. David.
Yes, yes, yes. Thank you very much, Professor Youssef, for this very interesting talk. Now the time is for questions or comments. So please, if you have any question, you can the unmute your mic and you can ask questions directly.
Yes, please. I have a question.
Go ahead.
Okay, thank you for this nice talk. Indeed, it's a general question. You mentioned many times the backward equation. Is there a forward analog of this equation?
Before, backward equation when is different from forward equation, because forward you give the initial condition and you go further in time. You go from 0 to time t to the origin. This is forward equation. But the backward equation, you comes from capital T to 0 in adapted y. You comes from capital T to 0.
It means somehow it's the time reversal.
No, not time reversal, because you need adaptedness. No, not it's different from time reversal. You need to. This is has an application in finance. For example, if you have something to do in the next July, you want to apply some option to buy something next July. What I do know to reach this wealth in next July? It means that you have something in the origin, in the picture, and you want how I can reach this. How I can reach this goal, okay, by adapted way in adapted way.
Yes. Okay, from a statistical viewpoint, is there a real difference, or it's just somehow?
Yeah, it's a real difference because
complementarity, or
no. It's the real difference because in forward we have only one process, one unknown process x, stochastic differential equation. But in backward you have two process, y and z. It means that you need some process to make y adapted. Because very, very important adapted. It means that you need to, yt must be ft measurable. This is, you need the help of something. You help of some adjunct process. You help of z. Then you have two unknown process for one equation in backward.
I see. So are there some results for weaker condition? Like you assume that you have local Lipschitz condition.
Yeah, you have a lot of condition, monotonicity condition, you have a lot. This theory maybe has about 30 years. It has a lot of condition given by several others, El-Karoui, Bahlali, Said Hamadan, Eddabi. Eddabi is one of these specialists in this field. You have something which is not Lipschitz, but you have something not function. It has something like measure instead of function. This is in some papers open.
Okay, thank you. Thank you very much.
Thank you very much, Professor.
Any other question? Please, from the audience.
Yes, please. If you can go to slide 10, please, Professor Youssef.
10.
10, 10, 1, 0.
Yeah. I understand. My slide. Okay. Okay. This one?
No, 10, 10.
Next.
Yeah, this one.
Okay. Maybe 9. What are the functions small and capital L? You
Small?
use some the function
okay.
small.
Okay. But this is the word. Just recall. No, this is for the story. This is the beginning of the fact. People use this function L. For me, the function L is arctangent.
Okay.
It's different. Yeah, for me, it's different. My function, this I replace this function by arctangent.
Okay.
But and I don't need this one is Lipschitz, but only locally Lipschitz, because arctangent is only locally Lipschitz.
Okay.
It's not, the inverse is okay, because the arctangent x minus arctangent y between x the absolute value of x minus y, but the lower bound, the derivative is 1. Of arctangent is 1 over 1 plus x2, and this one goes to 0. It means that this function is not Lipschitz. Our contribution is here. Okay, we replace the strict increasing of Hibon, Hu, Hamadan, Jihish by this, by something which is strictly increasing in locally Lipschitz. You can add this here, locally Lipschitz.
Okay.
I don't in my paper.
Okay, and the function capital LS, this function in equation 15. What is LS, capital LS?
What is capital LS?
In equation 15.
Yes. Ok. Oui, sans fonction. Oui, d'accord, c'est représentation. D'accord. Oui, don't. Yeah. You are right. I forget to give the expression of it's something like the one in El Karawi.
Okay. Some known function. Okay.
Some known function. Yes. You are right. Yeah.
Okay. If you can go now to slide 29, please.
Sorry to interrupt you.
Sorry.
29 is one?
29, yes. Okay. So C dash here, C bar, C dash depends on H. Okay. By definition, in equation 43, C dash depends on H, no?
C dash depends on. Okay, this is. Attendez. L'expression de C bar. Yes. No, this one, no, it doesn't depend. No, C dash, it doesn't depend on. This is the expression of this.
No, C dash in slide 29.
This one?
29, equation 43, C dash depends on H or not, or it is free of H. This C dash.
C'est barré.
Oui.
Dis-moi en français. This one.
Yes. It depends on H or free of H. This one.
No, I think it's free of H. It's free of
H.
It's free of H. Okay, it's free of. I think it's free of H because.
Because we consider the norm depends on H.
For each C bar, we exhibit
something which.
No. For each C bar.
For each C bar we have some H C bar such that this one for all H in this interval we have this.
Doesn't depend on H.
No, it doesn't depend on H. We have some bound, but for each H between 0 and C dash, you have this property. No, it doesn't depend because you take someone which is greater than this quantity, which it doesn't depend on H. Every for every C bar which is great, this is the bound, if you know. C0 is the bound. For every C bar, you have some hash C bar, such that for every hash here, you have this property 45.
But due to equation 43, I understand
Yes.
that for all H that you choose, you can find C bar free of H, such that we have
Yes,
the inequality.
Yeah, the inequality. Yeah, exactly. Yeah. But C bar, like exactly what Hamadan do in his paper. It means that this one is determined after, or Le Pelletier also, Le Pelletier in the Saint-Martin, so something like this. Okay. This one is determined after. We put C bar, but is determined here. C bar is greater than this bound.
But why you are sure in equation 45 that you can find HC bar greater than 0? Maybe HC bar equals 0, no?
No. HC bar, no, I give it in my, this is HC bar. Is this one?
Oh, okay. Minimum.
Okay, it's given explicitly why this quantity.
Okay.
So important is this bound, you know, this bound C0, and for every penalty, if you have this is the, yeah, it's greater than 0, strictly than 0. Yeah, you are right.
Greater than 0. Okay.
Oh, okay. Thank you very much.
Okay.
C'est qui? C'est Saïd, no? Who is asking this question?
There is no. The person who asking is Rafiq now.
Rafiq.
Okay.
That's right.
And can you give some details, general details, why you use the method of concatenation here? Why?
Why I use method of concatenation? Because I need some fixed. No, I need some fixed point theorem, because I need this phi. Phi. I need something like this. Excuse me. Yeah, I need this. I need that phi has a fixed point. No, because I define this application of phi. This I want to have this. Okay, it means that I need that this application has a fixed point theorem. Okay. And for this, I need the contraction. J'ai besoin d'une I need the contraction.
Okay.
Contraction mapping. So I choose my H such in such that this excuse me. This is the contraction. Okay, because you have 1 over.
You have something less than 1.
Less than 1, then you have a fixed point theorem. You have a fixed point theorem in this set. Okay. Then you have what you want.
Okay. Last question, please, in slide 6.
Slide 6.
Yes.
Yes.
Okay. If you take in equation 6, small t equals to capital T.
Yes, exactly. Small t to capital T to have you have this equation. To solve this equation, you solve it, you make difference, then you have this equation. Exactly.
No, I take just equation 6. I replace small t by capital T. So
yes, then you have this one. This one is equal to psi. Okay.
Yes, and at right, I have the mean of psi.
No, the mean of psi and 0 to capital T.
Okay.
To capital T.
Okay.
And you make difference, you have equation 7.
Okay.
Exactly.
Thank you.
This is exactly why you give me the solution of this equation. Okay. You take this, you apply it for capital T, and you make a difference, then you have exactly backward stochastic differential equation.
Okay.
Thank you very much, sir.
Okay. Thank you for you, Professor Youssef Ouknine, for this nice talk.
Okay, other questions from the audience? I think there was somebody who wants to ask or to give a comment. Who?
I have a question, please. A quickly question.
Go ahead, Reem.
Reem, yes. I am Reem Amami, if you remember me, Dr.
Yes,
Youssef.
I remember.
Yes.
I met you in Tunisia.
Yeah, I remember. Yeah.
How are you?
Fine, thank you, Reem. Thank you.
Thank you.
Very much.
I want to know if this problem it can be solved numerically using Python or MATLAB by taking an example of the function f. We can present the
Yeah. Some
by
algorithms to solve this because it involves the law. So
Yeah.
I'm not sure because the approximation of the numerical scheme for backward involving the law.
Yeah.
Maybe it's new and hard, I think, Reem.
Yeah.
I never
Yeah,
seen
it's
this.
new. Yeah.
No.
Yeah, the new, I think it's the arctangent. It's the first time that I see that we use arctangent.
Yes, because this arctangent have a lot of properties. This is increasing, strictly increasing process,
Yes,
strictly increasing function, and you can we can apply this double number is just application of mean value theorem.
Okay. And we
Because
can, in the real life, apply this problem, for example, in the mathematical finance.
yes. Yeah. We can replace this arctangent by some other function which is strictly increasing, the bounded, the derivative, strictly positive, a lot of conditions, but this is concentrated on arctangent.
Yes.
Okay.
Okay. Thank you so much.
Thank you,
I hope
Reem.
that
Thank
we
you,
can
Reem.
see you in Saudi Arabia.
Inshallah. Thank you very much, Reem.
Inshallah. Thank you.
Thank you very much, Reem. Thank you.
Other questions, please.
There is a question in the chat, Professor Mohammed Dabi.
I have a
Yes,
question.
the last one who said, what is a real life application of your work? This is the question from Mohammed Mudassar Hassan.
Yes.
Application, maybe perhaps in mathematical finance for pricing, maybe American option or something like this. But actually, I'm not interested in this. Okay, it's a new subject, so maybe is a new subject for the reflected backward stochastic differential equation. This application is by still envelope, something like this, is the pricing and hedging of American option or some sophisticated option in mathematical finance.
Okay. Thank you very much. Other questions? Have you any authentical reference for or research paper of its use?
Maybe this paper will appear, as I told you, this paper will appear in this journal, maybe in 10 days, very soon. Probability, uncertainty, and quantitative risk, 2025. This is a complete text of our work.
Okay. Other questions?
I have a question, Si Mohammed, s'il te plaît.
تفضل.
Right.
Yes, go ahead, please. Oh, sorry. Mohammed, go ahead.
Thank you very much, Professor Ouknine, for this very nice talk. I have maybe my question seems very naive because I'm not a specialist of SDE analysis. But if you can come back to slide 7. I have a question about just the form of the weak terminal condition in equation 8. Is there some motivation from finance to consider a weak terminal condition?
Yes.
Rather than a strong one. Of course, from a mathematical point of view, it's clear. But is there some explanation from...
Yes, you have an application in finance made by some people from Le Mans. I forget their name. No, not Hamadan. Matoussi. Matoussi is collaborator. Yeah, they give some application, and who else would give some pricing by quantile or something like it means that
Okay,
it,
well,
it evolves
they need a weak
yeah.
version of
Yeah,
the terminal condition.
Yeah, they need some probability that why the so-called var, the value at risk. It
Okay,
means that
okay.
they need the probability by that yt they pass some bound, and the probability is low, you know.
Okay,
Instead
risk management. Well,
yeah, risk management, exactly. Risk management.
Okay.
Yeah, exactly. Yeah, this
Okay.
is the.
Okay, thank you very much.
Other
Thank you very
question?
much.
So if not, Yusuf, I have just a naive question concerning when we are dealing with BSDEs. Uh, Sometimes we focus on uh, giving some probabilistic interpretation to some partial differential equations or some reflected partial differential equations. So mainly in reflected BSDEs, you can at the end in some under some assumptions give a probabilistic representation to a partial differential equation with directly boundary conditions or some reflected some conditions.
So-called variational inequalities.
Yeah. Regarding this problem, is there any something similar? Can one expect what kind of equations or deterministic equations for which BSDs can provide a probabilistic interpretation?
I know variational inequalities. Yes, we can do something, but with this probably maybe it's a new field. So up to now, I haven't seen some application in PDE. Okay, I saw the classical backward stochastic, replicated backward stochastic differential equation. This is for maybe for variational inequalities, but for this with involving the law, so maybe maybe someone by one at Valois and some people over here. This is well, Bangman, yeah, some non-linear, strong non-linearity. Okay, the so-called quasi-variation, quasi-variational equation, something when the coefficient also when the coefficient contains the unknown, you know, when the unknown function. Quasi something. Ben Ashur, Valois in the one paper by these people in this big bank process, maybe perhaps.
Okay, other questions, please, from the audience. So if not, thank you very much, Professor Ouknine, for this new subject and this interesting, probably motivations for PhD students who wants to go further on this direction. Maybe this will be new directions, or some people can find new directions from this paper. So thank you very much again. Thanks to the audience.
Thank you very much for all the audience. Thank you, Professor David. Thank you, Professor Agesh, for your invitation. I am happy to be with you, to share with you this talk, and see you next week.